How much does a large language model actually know about sound if it has never heard a single waveform? In the world of AI, we've seen a massive surge in large audio language models, or LALMs. These systems typically use an LLM as a cognitive backbone, paired with an audio encoder to bridge acoustic features into a linguistic space. But here is the critical question. Does the choice of that LLM backbone actually matter, or is the performance just a result of the audio encoder and the training data? A recent research paper titled, How Auditory Knowledge in LLM Backbones Shapes Audio Language Models, tackles this head-on. The researchers wanted to determine if the auditory knowledge encoded during text-only pre-training, essentially, how the model understands descriptions of sound, influences its eventual performance as a multimodal audio model. To figure this out, the team developed a holistic evaluation framework consisting of 3 distinct settings: direct probing, cascade evaluation, and audio-grounded evaluation. First, they created AKB-2000. This is a curated auditory knowledge benchmark featuring 2,000 multiple-choice questions across 6 categories: music, sound, paralinguistics, phonetics, audio quality, and technical knowledge. This isn't just about identifying a dog barking. It tests deep technical concepts, like the power spectral density of white noise or the specific intonation patterns of English questions. By running 12 open-weight models and several proprietary baselines through this, they could profile the auditory IQ of the LLMs in a purely textual environment. Second, they used a cascade evaluation. In this setup, they don't feed the LLM audio. Instead, they use a high-quality audio captioner, like Gemini 2.5 Pro, to describe an audio sample in detail. The LLM then has to answer a question based on that text description. This tests whether the model can actually apply its internal knowledge to reason about real-world audio scenarios. Finally, they performed an audio-grounded evaluation. They took these same LLMs and fine-tuned them into full LALMs using a self-distillation framework called DISTA. They paired the LLMs with a Whisper Large V3 encoder and a Q-former connector. Crucially, they froze the LLM parameters and the encoder, training only the connector. This isolated the LLM backbone as the only variable, allowing them to see if a model that scored high on the text-only AKB-2000 benchmark actually became a better audio model after training. The results were revealing. First, there is a massive variance across model families. In the open-weight category, the QN family consistently outperformed Llama and Almo. In fact, when using an identical training recipe, the choice of the base LLM alone resulted in a performance difference of over 10% in the final audio model. This proves that the backbone isn't just a passive processor, it's a fundamental determinant of the system's ceiling. Second, they found a very strong positive correlation between text-only performance and audio-grounded performance. This is a huge takeaway for researchers. You can use a lightweight, text-only benchmark like AKB-2000 to vet and select your backbone model before you ever spend the massive compute required for multimodal fine-tuning. However, the study also uncovered a significant blind spot in LLM pre-training, phonology. Across every single model, performance plummeted in tasks involving pronunciation, stress patterns, and rhymes. For example, models struggled to identify if cat and hat rhyme. This is because LLMs learn semantic correlations between tokens, but they have no concept of the acoustic realization of those tokens. They know what a word means, but they don't actually know how it sounds. Perhaps the most surprising finding is the cascade bottleneck. The researchers found that a simple pipeline, a strong captioner feeding a strong LLM, could actually match or even beat several state-of-the-art end-to-end LALMs. This suggests that current end-to-end systems are actually being bottlenecked by their audio encoders. The LLMs have the reasoning capability to handle the audio, but the encoders aren't preserving enough fine-grained detail during the alignment process to let that capability shine. In summary, the auditory knowledge an LLM acquires from reading about the world fundamentally shapes its ability to understand the world of sound. If you're building an audio system, the backbone you choose is a first-order design decision. While we've made great strides in multimodal alignment, the phonological gap remains a frontier that will likely require new, phonology-aware training strategies to solve.